if you have an equation, you can always plot points to sketch the graph, but sometimes it's helpful to have an idea even before you start plotting points what the basic shape is going to be. And there's there are patterns that you can recognize in the from the formulas as to what the shape is going to be. So one example would be absolute value functions. If you see an absolute value, generally it's going to be have a V shape, and the vertex or the of the V is going to be whatever value of x will make the what's inside the absolute value equal to 0. So in this example here, f of x equal absolute value of x minus 2 plus 1. The vertex is going to be when x is equal to 2. So when you can plot points, but in order to get the full V, it's going to be helpful to plot include x equal 2 as well as some numbers less than 2 and some numbers more than 2. So we make a table of values. Here's our vertex, and I put 0 and 1 inputs are less than 2, 3 and 4 are numbers that are more than 2, and then plug into the formula and plot the points. Okay, and so you end up with a V-shaped graph. Piecewise functions. The height of a rocket will have a different formula before and after fuel runs out. So if you want the full formula for the height of a rocket, that would be a piecewise function. For some procedures in calculus, it's useful to write absolute value functions as piecewise functions. This is a more generic example here. We have a piecewise function. F of x equals negative x if x is less than negative 2. If it's equal to 1 minus x squared if x is between negative 2 and 1. And it's equal to x minus 1 if x is greater than 1. So we have, this one actually have 3 different formulas depending on what the value of x is. So looking at these formulas, we perhaps can see that 2 of these are going to be straight lines, and the other one's going to be a piece of parabola. So if you know something about the shape, then you don't have to plot so many points. So we want at least, for a straight line, we want at least 2 points, and we want to include the values on the boundary between 2 different formulas to find out if there's going to be a gap there that tells us whether to have a closed circle or an open circle. So we're going to use negative 2 on both of these formulas here, and then we need one other point, let's say negative 3, one other number that's less than negative 2. So I'm going to pick negative 3 and negative 2 for the first formula. The middle formula, again, I want to include the 2 boundary points, the negative 2 and 1, and also some points in between, so, or at least one point in between. So I'll say negative 2, 0, and 1. And last formula, again, we want to include the boundary point, even though it's actually, even though the boundary actually applies to the formula before, but we want to include the boundary to know whether it connects with the previous formula or whether there's going to be a gap there with an open circle. So we want to include 1, and then we know it's going to be a straight line. We just have to include one other number that's bigger than 1. So I use 1 and 2. Okay, so for the first formula is f of x equal minus x. So minus the negative 3 is 3. Minus the negative 2 is 2. The second formula, we want 1 minus x squared, 1 minus negative 2 squared. 1 minus 4 is negative 3. That does not agree with our previous input of negative 2, so that tells us there's going to be a gap there. I have an open circle and a closed circle. F of 0, 1 minus 0 squared, 1 minus 0 is 1. F of 1, 1 minus 1 squared, 1 minus 1 is 0. And then the last formula, if we put in 1 there, we get 1 minus 1 is 0. So here the 2 agree, so there's no gap. We'll have a closed circle. F of 2, 2 minus 1 is 1. And then we can plot the points. So this is 3 to the left, up 3. Go from the center, go 3 to the left, up 3, put a dot there. Next point, 2 to the left, up 2, 2 to the left, up 2. We put an open circle there because of the gap, and then you want to connect the dots. So this will be the first part of the graph. And then next point, 2 to the left, down 3. That's this point here. This was the middle formula actually includes the boundaries, so we can put a closed circle there. And then we have 0 left to right, up 1. Put a little dot there. 1 to the right, up or down 0. Put a little dot there. The last formula, 1, 0, it's the same point. It's already plotted. 2 to the right, up 1 is this point here, and then connect the dots. So that's our graph of a piecewise function. Greatest integer function. Double square brackets means the greatest integer less than or equal to x. So this function f of x equals greatest integer less than or equal to x. For this function, it'll be helpful to include some decimals in our inputs to give us an idea of the overall pattern. So if x is 2, x is 0, the greatest integer less than or equal to 0 is 0. If the integers are like 0, 1, 2, 3, etc. Also negative 1, 2, negative 3, etc. 0.3, greatest integer less than or equal to 0.3 is 0. 0.7, greatest integer less than or equal to 0.7 is 0. So actually the greatest integer less than or equal to 0 point anything is going to be 0. But as soon as you get to 1, then it goes up. So the greatest integer less than or equal to 1 is 1. Greatest integer less than or equal to 1.5 is 1. Greatest integer less than or equal to 1 point anything is going to be 1. Okay, so then we can plot the points. We have 0, 0, and then 0.30, 0.70, and then I put an open circle here because 0 point anything is going to be it's going to be 0, but then as soon as you get to 1, it jumps up. So there's going to be a gap there in the graph. It jumps up to 1. And then the greatest integer less than or equal to 1.5 is also 1. So that's probably enough to see the pattern. It's going to be a staircase type pattern, and you just continue the staircase in both directions. This actually has some applications. The postage rates can be expressed in terms of greatest integer function. For example, if the postage rate is 50 cents for the first ounce or fraction of an ounce, and 21 cents for each additional ounce or fraction of an ounce, then P of x will be 50, the postage price will be 50 minus 21 times the greatest integer less than or equal to 1 minus x. And this formula applies for x greater than 0. Reciprocal function. This is actually a hyperbola. We studied hyperbolas already, but this is would be another example of a hyperbola. F of x equal 1 over x. And we'll get into some more when we get into. We'll do more with rational function or fractional functions toward the end of the course. That are, and a lot of those will be hyperbolas. Okay, so f of x equal 1 over x. So f of negative 100, 1 over negative 100, f of negative 0.01, and we can see that if x is big in absolute value, it's going to be closer and closer to 0. X over negative, if x is negative a billion, 1 over negative a billion is even smaller, right? It gets closer and closer to 0. If x is negative 2, 1 over negative 2 is negative 1/2. If x is negative 1, 1 over negative 1 is negative 1. If x is 0, 1 over 0 is undefined. If x is 1, 1 over 1 is 1. X is 2, 1 over 2. X is 100, 1 over 100, or 0.01, be close to 0. So we can plot the points. The negative 100 and positive 100 are not convenient to plot. So I didn't plot them, but you can see that I put those in to just sort of demonstrate that it's getting closer and closer to 0 as x gets big in absolute value. I plotted negative 2, negative 1/2. That's 2 to the left, down a half. 2 to the left down a half, 1 to the left down 1, that's right here. 0 is undefined, so I can't cross the y-axis where x is 0. 1 to the right up 1, and 2 to the right up a half. I actually planted an extra point here. Yeah, I planted a couple extra points too. But that's enough to see the pattern. You want to connect the dots, and you can't cross the y scale. You can't cross the x scale either, because on the negative side, you have 1 over negative a billion, or 1 over negative a trillion, 1 over negative a quadrillion. It's going to get closer and closer to 0, but it's never going to become positive. It's going to stay negative, so it doesn't cross the y scale. And same on this side. If you have 1 over a billion, or 1 over a trillion, 1 over quadrillion, it's still going to be positive. It'll get closer and closer to the y, the x-axis, but it doesn't cross. And likewise, it can't cross the y-axis either. It gets closer and closer. So that's a hyperbola. And you may remember that hyperbolas have asymptotes. The x-axis here is actually one of the asymptotes, the horizontal asymptote, and we have a vertical asymptote here where x is equal to 0. That's the y-axis. Okay, so that's okay. So here's some more functions. Polynomials, we'll study those in more detail later, but we've already studied straight lines. For example, f of x equal 3, or f of x equal 2x minus 3. This is the 2x minus 3 has slope 2. F of x equals 3 has slope 0, horizontal. They're straight lines. If you have a degree 2 polynomial that has an x squared in it, that's a quadratic function. That's going to be a parabola. It has one hump. The straight lines have no humps. The parabolas have one hump. If you have a degree 3 polynomial, you could have up to 2 humps. This one has no humps. It's kind of the hump kind of flattened out on this one, but this is x cubed minus 2. But if you have x cubed minus 4x squared, you'll have two humps there. There's one hump here and one hump there. Degree 4, x to the 4th, or x to the 4th minus 13x squared plus 36. Highest power of x is 4. X to the 4th, the humps kind of flatten out again. X to the 4th minus 3x squared plus 36, you have 3 humps. There's one here, one there, and one there. So degree 4 has up to 3 humps. But we'll study polynomials in more detail later in the semester. Square roots, we've already sort of mentioned those. The two most common ones that you might run into would be a semi-parabola. F of x equals square root of x. Looks like this. It's a half of a parabola opening to the right. And the square root of 1 minus x squared would be a semicircle. The full circle would have a lower part here, but this is the upper semicircle. And that concludes this presentation.